have you ever stopped to think about how we build software and if it has anything at all in common with how our own brains work? Well, we're about to dive into a pretty amazing connection between the evolution of human thought and the evolution of code. And trust me, there's a surprising link here that's probably going to change how you look at both.
Okay, so it all kicks off with this paradox, a real mystery. See, our minds, they evolved to see the big picture first, the general idea, and then fill in all the little details. But the software we write? It's the complete opposite. It started at the most nitpicky, specific level possible and has been crawling towards generalization ever since. How on earth can these two timelines be such perfect mirror images of each other?
I mean, just look at these two paths. For us, human cognition, we start super general. We get the concept of a tree way before we can point out a specific birch or a pine. But with programming, it's totally backwards. We started with this hyper-specific machine code, assembler, and only very slowly built our way up to big general concepts like object-oriented programming. They're going in opposite directions. So what's going on here?
To really get to the bottom of this, we've got to break down each path. So first, let's tackle the one we're most familiar with, our own minds.
This is going to take us way back to a time before complex language, to the very bedrock of how our brains figured out how to make sense of the world. And it turns out, thinking in these big, broad strokes, it wasn't a bug. It was a feature, a superpower, even.
And you know what it all comes down to? One word: survival. Think about it. For our early ancestors out on the savannah, seeing some blurry shape in the grass and your brain instantly screaming "predator" was way, way more useful than spending precious seconds going, is that a lion or a tiger? Generalization wasn't just helpful. It was the difference between becoming lunch and living to see another day.
And this way of thinking, it wasn't some random accident. It was driven by some really key factors. It was an absolute evolutionary necessity for reacting fast. It was also a brilliant energy-saving strategy for the brain, so you're not starting from scratch with every single thing you see. And, at our core, that's just what our brains do. We are pattern recognition machines, hardwired to find the general rule.
Cognitive psychology actually has a name for this. It's called prototype theory. The idea is, instead of having some strict mental checklist for what makes a bird, has feathers, has a beak, flies, our mind just creates a prototype. It's like a mental image of the most bird-like bird you can imagine, maybe a robin or something. Then we just compare everything else to that prototype. It's fuzzy, it's efficient, and it's an incredibly powerful way to sort the world.
Okay, let's hit pause on the brain for a second and switch gears. We have to look at the other side of our paradox. Because for decades, programming was chugging along just fine, and then it hit a brick wall. A crisis of complexity so huge, it forced a total reinvention of the entire field.
By the 1960s, this was the cold, hard reality. As our ambitions for what computers could do got bigger, the software projects just became these massive, tangled messes of code. They were brittle, a nightmare to maintain, and just crushingly complex. People started calling it the software crisis, and it was painfully clear that the old way of doing things, that super detailed, specific way, it just wasn't working anymore.
So, to fight back against this chaos, programmers had to find a way to get further away from the machine's details. The journey started with assembler, which is basically just talking directly to the hardware. Then we got procedural languages like ALGOL, which let you group instructions into steps. But the real game changer, the big leap, was object-oriented programming, or OOP. It bundled data and the functions that use that data together into these neat little packages called objects.
And what was the whole point of OOP? It was to manage complexity by, wait for it, modeling the real world. By creating these little software objects that act like real-world things, like a car object that has properties like color and can do things like drive, programmers could finally build systems that made more intuitive sense. Modeling the world with general categories. Does that sound a little familiar?
And right here, this is it. This is where our two separate stories finally smash into each other. This is the big aha moment, where the way our brains evolve to see the world and the way we invent it to build our software suddenly and just remarkably line up.
Prepare to be a little bit amazed because the parallel is stunning. We can literally map the cognitive concepts we all use every day to understand the world directly onto the core ideas of object-oriented programming. They're basically two sides of the exact same coin. Just check this out. Our mental category or prototype of a bird, that's a class in programming. It's the blueprint. A specific bird you actually see in your backyard, your perceived object, that's like an instantiated object in code. It's a real thing created from that blueprint. The shared characteristics of birds, like flying and chirping, those are its attributes and methods. It's the same pattern. It's incredible.
So now, finally, we can solve the paradox we started with. We have all the pieces of the puzzle. Why are the timelines the reverse of each other, even though they ended up in the exact same place? Simple. For the brain, the path was carved out by biology. Abstraction had to come first. It was an evolutionary necessity. Fast, general decisions kept our species alive. Plus, our brains are just neurologically built that way. It's our factory default setting.
But for software, the path was dictated by technology. Early computers were incredibly weak and clunky. They just didn't have the horsepower to handle the extra work, the overhead, of abstraction. So detailed, down-to-the-metal code was the only way to go. And honestly, the early problems they were solving were simple enough that you didn't need abstraction. OOP only became a necessity when the problems got too big and the hardware finally got powerful enough to support it.
And that is the resolution. It's so cool. The brain and the computer, they faced totally different problems on totally different timelines. One was dealing with the complexity of survival, the other, the complexity of logic. And yet, both of them, when pushed to their absolute limits, independently discovered the exact same elegant solution: abstraction.
And that leaves us with one last really big question to chew on. If nature, through evolution, and humanity, through engineering, both arrived at abstraction as the ultimate tool for handling complexity, could it be that abstraction is the universal language of intelligence itself, whether that intelligence is grown inside a skull or built inside a machine? It's something to think about, isn't it?